Good morning. We have Katie Ferreter from BMO. I was going to give you a great talk this morning about BMO's work with Waterloo.AI. So just to give you an intro on Katie. Katie is the head of technology research and innovation at the BMO Financial Group. This role sees her seeking out knowledge of emerging technologies and determining their maturity and applicability for BMO. She runs a team that undertakes research internally, as well as partnering with institutions and organizations that are shaping and framing the future of technology. So Katie, I'll turn it over to you. Thanks for being part of this event today.
Thanks so much. I'm absolutely delighted to be here. I'm sharing a presentation on my screen. Hopefully you are all able to see it. I've got my thumbs up, so I am good to go. I hope you're all having a really good morning and you are as excited about the lineup of topics and speakers today as I am. Massive thanks to the Waterloo.AI Institute for inviting BMO and putting together such an amazing event. We're really proud to be partnered with Waterloo.AI and more specifically the SWAG, Software Architecture Group at the university. As Harold mentioned, I'm Katie Ferreter and I run the Technology Research and Innovation team at BMO. We were formed nearly 3 years ago with the aim of exploring emerging technologies and understanding their applicability for the financial services industry. We look to foster an innovation culture by partnering with our internal teams and providing knowledge about the latest technologies to them. Part of this work sees us partner externally with organizations like the Waterloo.AI Institute to foster an innovation ecosystem in North America and to learn from intelligent minds working on interesting problems. In addition to research institutions like Waterloo.AI, we explore innovation with the private sector. In this case, we're looking for companies with niche skills, usually skills that we don't have yet in-house, or companies that have solved an interesting problem that allows us to adopt that problem, so that buy versus build in terms of adoption. We utilize government body funding for our innovation activities. This funding comes from bodies like the Ontario Centres of Excellence, NSERC and MyTax, who I believe we will be hearing from later on. And then this goes directly back into Canada, enabling us to create a collective community to continue to innovate and grow. There are amazing technology innovations happening here in Canada, and I think it's really important that we come together to support them. So why do we research? Well, we want to understand and accelerate our understanding of what's emerging through those diverse skill sets and through different perspectives. Research institutions tend to be ahead of the curve, whether that's theoretical or applied concepts. And universities like UW are looking at topics and capabilities that are not yet mature and are typically not yet used in the private sector. So partnering allows us to remove blind spots and keep an eye out on what's coming and how it is maturing. I often like to say that the AI Institute is the perfect Canadian fit for the BMO Technology Research and Innovation team. If you look at the Kitchener-Waterloo area, you see innovation everywhere. Waterloo has been coined the smartest city, with a young, vibrant, talented population creating and discovering at the university, in innovation spaces like Communitech, and the many, many startups. I also want to highlight the use of problem statements and that part of the collaboration. These have been a game changer for BMO. Waterloo.AI offers the ability to co-create on a problem statement that then goes out to researchers as a call for proposal. This enables us to obtain broad and a varied set of proposals and ways to solve or look at the problem in question. I love the phrase, "You just don't know what you don't know," and it's so true in this case. I never want to limit the problem or the potential solution to something that BMO or I is already aware of. Instead, we want to see what the professors and students think and how they would frame a topic. This allows us to continue to remove our blind spots and figure out a better way to solve a problem. So, the software integrity problem. Time to market, quality of the applications, and cost of this quality are a continuous balance for organizations. When we think of banks more specifically, we continue to digitize our capabilities, and good quality software becomes increasingly important. People's finances are a serious topic, and they need to be able to trust the integrity of the institution that's holding them. That now means also trusting the applications they use to bank, as digital banking becomes more widely adopted by consumers. The Consortium for IT Software Quality, or CISC, has estimated that poor software quality cost US organizations $2.8 trillion in 2018 alone. So this is clearly a problem with the potential to save a lot of money if it is solved for. There are many areas of the software development lifecycle to consider, whether that's scope, your requirements, quality assurance and testing, implementation, or development. We recognized a significant amount of time, money, and work goes into preventing and resolving defects within BMO systems and code. And so we decided to focus in that space for our initial research collaboration. So why is dealing with defects a big cost in building software? They can be expensive to find and fix. So picture this. You have quality assurance teams that are building and running automated testing. They're creating test cases and they're carrying out manual testing to identify and raise defects. Developers spend their time searching for these bugs in their code once they are raised, and then they need time to fix and redeploy the code. If there are multiple applications and integrations, then multiple development teams are tied up figuring out the failure point. Project managers spend time documenting the bugs, reporting on these bugs, and estimating the time to resolution and communicating this information to steering committees. These are just a few examples of roles that would be involved in this defect process. And so pretty soon you have large teams that are being paid to manage this issue. The second reason here is it's time consuming. This translates to more money being spent and therefore projects not meeting their budget. It also means delays in releases and impacts on overall timelines for programs. And then the third and arguably the worst case scenario is a bug that goes undetected, which can severely impact the end user's experience. We wanted to research the ability to predict key metrics using AI and machine learning with the overall aim of reducing bugs in our code. We decided to explore and to examine if we can use existing data to analyze and predict where defects may exist in code. So which files are likely to contain a defect, and then drill in another layer and identify more specifically where a bug is likely to be present within the file so that the developer can fix it more quickly. So what predictions do we want to make? If we drill in another layer, we're considering items like priority, severity, and cost to fix. So number one, where the bugs exist. So in this case, we want the file, if possible, the specific lines of code within the file. Two, the size of the required fix. Is it small, medium, large? How many lines of code are impacted? Three, the experience needed to fix. Could a junior developer manage this fix, or do we need someone more experienced? Thinking of efficiencies here and how you could best utilize your development team's resources. And 4, the severity of a bug, with 1 being a showstopper through to 4 being low priority. And again, this is the aim of prioritizing the work that you do first. We started by investigating the use of traditional prediction models, so linear regression and neural networks, to generate predictions for the key values mentioned above. So again, that's the existence of a bug, the size of the required fix, the experience needed to fix, and the severity. This work began with open source solutions to build and train an initial model. We used 11 open source Java-based projects, as our test BMO code is also in Java. This was to allow us to show some results and get an idea of how well this might work in practice. Some of the key results include, we can see that predicting the priority, the bug fix size, and the bugginess can be done with some effectiveness, but the prediction of developer experience is significantly harder to predict. There was an average bugginess AUC, or area under the curve, of 0.33. For context, the AUC provides a value between 0 and 1, where 1 indicates perfect predictions and 0 indicates that the predictions are 100% wrong. We had an average priority accuracy of 41%. This is equal to the number of correct predictions divided by the number of false predictions. And we had a median fix size, mean absolute error, or MAE, of 15.6. Mean absolute error provides the average distance between the predicted value and the actual value. 0 is the best case here, and so the higher the number, the further away we are from an accurate prediction. You can see that the MAE for developer experience is much, much higher than the median fix size. Potentially, this is because fixes are not signed by experience or title, but rather how much a developer worked on a project. The models could be further improved with additional data. I think that is our age-old machine learning problem, never enough data, as well as the use of significantly more independent variables. You can see 30 plus variables in some prediction models versus the 3 that we used for this initial research. The 3 variables we had were cyclomatic complexity, which indicates the paths or branches through a particular function. And we're currently extracting this using SonarQube. The second variable is the lines of code, where a Python script reads files and counts the lines of code. And the third variable is code churn, which is indicated by counting the number of lines added and deleted in a particular time period. A more recent topic and area of focus of this research is in semantic learning models. And this is the development of a model that uses the code within the program files as training data in place of the statistical-based characteristics that were previously used. This area of focus leveraged an open source library code Defects that aims to capture the semantic meaning of a segment of code, which in turn helps to enable the ability to build machine learning pipelines for more applicable use cases like code retrieval, classification, and tagging. Results were less accurate than the more traditional models, so the linear regression and the neural networks, but the technique is relatively new, and so it may be further improved with additional research. On the BMO side, we worked with Gemma, May, and Mike, our wonderful dedicated researchers at SWAG, to gather the right data, including information on defects using our defect repositories, metrics from our source code files, and relevant information from the development process at BMO. We used the same fundamental prediction model and applied it to BMO data. There have been a few early learnings here. One, the need for consistent data is so important. And two, you need a large enough data set to train the model. As with many other AI problems, data gathering was and continues to be a difficult task. AI is only as good as the data it is trained with. So you can think of this as, in some cases, our teams might raise defects differently, and code commits may be different by different development teams. The amount of defects and the size of the source code, as well as how many iterations or changes it has gone through, are also an impact. Running the model is currently manual, but in an ideal scenario, this would be automated. So you could incorporate it into part of your software development lifecycle, maybe so that it runs as part of developer unit testing or when a significant change in the code is made. And then outcomes, so results of running the model. How did it do? Well, this is pending as we gather more consistent data. We think that ideally you need 1,000 to 2,000 well-documented bugs with standard data to start to see an impact or more accurate results. This research will continue with the following main objectives. Researching and implementing a bug localization model, which uses state-of-the-art deep learning techniques to locate the lines of code that are at risk of causing an issue or bug. We can see this as an additional layer from our current state, which is locating the file with a bug. Researching and implementing more sophisticated methods that use abstract syntax trees and the application's code to predict bugs during the development stage. This objective can be seen as an extension of the research into the use of semantic learning models. And then further training on BMO code to create continued predictions, measure their accuracy, and understand the impact of the prediction for the development teams. Does the code quality improve? Do we see a reduced time to implementation? Basically, we want to measure if a developer is getting those prompts and hints as to where a bug may exist. Does it reduce our time to implementation or reduce the time spent in development and QA? I'm learning so far. I think AI maturity is needed to make this more widely adopted. I also think the same can be said for a lot of AI applications and initiatives. Currently, the model has to be trained for each specific project. So this is regardless of similarities like the same language of code being used or a similar application, like they're both APIs, for example. So while narrow AI continues to be the norm, we might need to choose the highest priority projects to train and run. So for example, we might choose customer-facing applications versus internal employee applications. This research opened our minds to other ways of using AI for the software development lifecycle, and I'll just highlight two of those here. We could use natural language processing to examine requirements and design documents and to provide prompts to developers of places that they might be getting off track or that code doesn't match a part of the proposed design. We could also use natural language processing to examine other code in repositories for reuse of code. And here you could recommend the use of approved bug-free lines of code to save some time and take some stress away from the development process. I've said it before in the last 20 minutes, but I'll say it again. Consistent documenting and recording of data is going to be essential to enable AI. And I think we're pretty good at this when it comes to certain data types or data sets, but with others, less so. So it's something that we'll continue to work on. And then fine-tune our understanding of the development process and make sure that we're solving for the right problem. For example, we've learned this time around that it's not enough to tell a development team that there are 30 bugs in their code. but it's way more helpful or impactful if we tell them that there are 4 showstoppers, and therefore that's where they should go first. Just want to say a massive thanks for coming to listen to this talk today. We're really happy to be working with the Waterloo.AI Institute and looking at interesting problems in AI. Hopefully we'll be back someday soon to discuss our results as they continue to unfold. And I would love to connect with any of you on LinkedIn and have some AI-driven conversations. I'll pass it back to our wonderful hosts at the Waterloo.AI Institute. Thanks again.
Awesome. Thanks, Katie. Thanks so much. I've got a question for you here. Throw you in the deep end a little bit.
Go for it.
So how much AI did yourself or your team know before they started working with Waterloo.AI? Did they have to know and talk and walk the AI language, or could they just bring their challenge and problem forward?
Definitely the latter. You could just bring your challenge and problem forward. I think something that, again, continues to amaze me about partnering with the Waterloo.AI Institute is the amount of time that goes into educating partners. Things like reverse co-ops, stuff like this at Industry Day, and really, again, back to that problem statement generation. So the ability to work with people at the Waterloo.AI Institute to craft a problem statement means that you don't have to have a deep knowledge of AI, and part of this can be a learning curve or growth for your team and for your company.
Excellent. Thanks for those kind words about Waterloo.AI. So now looking internally, what's your challenges in selling AI up to your network? Because obviously decision makers and things have to be made. So how do you deal with those challenges?
Well, I think one challenge we see specifically maybe in banking, but I would imagine in all regulated industries, as well as maybe all customer-facing applications, is the need to have quite clear transparency and explainability in our AI solutions and applications. Without that, I think it's quite a difficult sell to say that we should be utilizing some of these concepts. And so it's certainly something that we're focusing on so that the applications that we use can be approved and can be seen as being transparent. So I would say that's one thing. And then the second thing is education within different teams. AI is still relatively new in its pure sense, so using maybe machine learning and deep neural networks. And so there's an education piece that needs to take place at every level of the organization, and it's certainly something that I'm still learning about too.
Excellent. Excellent. So one last question. Is there an early victory, an early thing that you've been able to communicate through your organization?
Well, the ability to even be able to run the model that's been created on BMO code for us is a victory. And so although we need to continue to build on the data that we have, the very fact that we can already show that this is working and that this is running tells us and tells our leadership and the other teams that we talk to that this is quite real. And so we're not dealing with something that's theoretical or conceptual. It's something that can start to make an impact and that you can start to utilize today.
Okay, this is an interesting question. If there's a bug in the code, how do you train code to find its own bug?
That is a brilliant question. One I wish I had the answer to. I don't know if we can run the model against the model itself, but yeah, that's a funny one. I do not know how we fix bugs in our machine learning code or how we get that code to identify that it has a bug in itself.
Okay, well, great. Well, thank you so much